before I turn it over to today's speakers. First, I want to thank you for joining. Today's webinar is being recorded. So a recording along with presentation slides will be posted to our website in about 10 business days. We will send an email out once those are posted to our website as well, but feel free to check back. Everyone is on mute, so please submit your questions via the question function, and we will cover those during the Q&A at the end of the presentation. Since we do have multiple speakers today, I encourage you to indicate who your question is for when you're submitting them, so then there's no guessing game. Also, we do host webinars monthly, and sometimes we have 2 a month. So I encourage you to check back to our website for future webinars and different topics that we have. I also encourage you all to sign up for our monthly newsletter, which we do send out at the beginning of each month. So on that note, I'm going to turn it over to Erica Sutherland. Erica is a Technology Development Manager for the Fuel Cells Technology Office, responsible for hydrogen delivery activities. Erica?
Thank you, Allie. We're happy to present this webinar today on the Hydrogen Student Design Contest, and I'd like to introduce Emmanuel Wagner. He is the Contest Manager for the Hydrogen Education Foundation. As Contest Manager, he develops the contest theme, raises sponsorship, facilitates the contest, and is the prime point person for the student teams. He also manages the HEF outreach activities for the Department of Energy's $1 million H-Prize, which launched just last week. Employed by the Washington, D.C. Association Management Company Technology Transition Corporation since 2009, Emmanuel is also engaged in the Industry Trade Association's California Hydrogen Business Council as the Associate Director, as well as the Biomass Thermal Energy Council as Programs Manager. Emmanuel?
Hey, Erica, thank you so much. Ellie, if you actually want to advance the slides. First of all, I would like to thank the Department of Energy's Fuel Cell Technology Office and the National Renewable Energy Laboratory for their support of the contest and for hosting this webinar. Their help over the years has really been essential to the success of this contest. So next slide. The Hydrogen Student Design Contest is one of several projects of the Hydrogen Education Foundation, or HEF for short. The HEF is a charitable nonprofit organization based in Washington, D.C. and dedicated to promoting clean hydrogen technologies through innovative national competitions, national hydrogen and fuel cell events, and educational programs to encourage environmental stewardship, to help improve energy security, and to create green jobs. Now, 2 key activities of the HEF are the Hydrogen Student Design Contest, which I'll cover in a moment, and the H2 Refuel H-Prize. So the H-Prize, as we've just heard, was launched last week, and it's a $1 million competition to design, build, and test a small-scale hydrogen refueling system. In essence, the contestants from around the United States are challenged to help create a system that provides early adopters of hydrogen vehicles an affordable fueling station for their home or community. If that sounds something if that sounds like a challenge that you would like to take on, check out the H-Prize website at hydrogenprize.org. And if you want to learn more about what else the HEF is doing or our current programs, check out hydrogeneducationfoundation.org. If you want to receive timely updates on hydrogen developments around the world or on HEF's activities like the contest, consider liking the foundation on Facebook or follow us on Twitter at H2NU. So next slide. So let's talk about the contest. It's an annual competition for undergraduate and graduate students from around the world, supported by DOE's Fuel Cell Technology Office and NREL, and the contest challenges student teams to plan and design hydrogen energy applications for real-world use. For the most part, the competition has a strong technical focus, but it does include interdisciplinary sections such as business, economics, political science, chemistry, and others. Next slide, please. So the first contest was launched in 2004, and since then it has received support and funding from government institutions and private entities. Past themes include designing residential fueling systems, hydrogen communities, commercial-sized stationary fuel cells. Actually, the 2005 winning design for a fueling station was built at the Schatz Energy Research Center at Humboldt State University and it was partly financed by Chevron and has recently been upgraded to allow for 700 bar fueling. So if you're ever in the area, do check it out. Contest participants come from around the world, and the number of teams participating range from a dozen to more than 50. Students choose to participate because there are a few benefits in doing so. For example, the winning team or teams receive a travel stipend and a conference registration to a major industry conference where they may present their design at a session to industry attendees. They can also publicize their entries in the International Journal of Hydrogen Energy, which is a major hydrogen energy publication used by engineers and researchers. Other prizes can develop during the contest, for example, this webinar, and we try to develop opportunities to highlight the participants wherever possible. Of course, a key reason to participate is also getting a hands-on experience with developing a design or a plan which is reviewed by industry experts, and for the students it's a great way to get in front of industry representatives, to get their name out, and to have some face time with potential employers. Next slide. So the last year's contest received generous support from government agencies like DOE's Fuel Cell Technology Office and NREL, and it also received in-kind support from the International Association for Hydrogen Energy, the CCAT, the Connecticut Center for Advanced Technology, Fuel Cells 2000, and the Northeast Electrochemical Energy Storage Cluster. So thank you all to those organizations. Now let's get into last year's theme. It was, on the next slide, it was the development of a hydrogen drop-in fueling station. Why was it picked? Well, really because one of the key issues in infrastructure build-out is to know where to put stations for the vehicle owners to refuel their car. And currently there's a lot of analysis that is being done to make sure the early adopters of the vehicles have a convenient access to refueling stations. But of course there are really no guarantees. So one approach is to avoid that early drivers will be limited by range, by the lack of infrastructure, by developing such drop-in fueling stations that allow greater range in areas of low penetration. So on the next slide, we'll see what drop-in means. It's that stations should be easily transportable to another location once demand in the areas is large enough to justify an investment in a stationary fueling station. So furthermore, they should have comparatively inexpensive costs to be built in great numbers and require low maintenance and easy permitting. And finally, this goes for all of our contests, it's not an R&D contest, so all the components in the design have to be commercially available. Next slide. So the 2014 contest had 7 sections, which needed all to be addressed in detail. The most important section is up front, of course, the design of the station. It was supposed to provide 100 kilograms of hydrogen per day and be able to refill at about at least 6 cars per hour. The system had to either produce the fuel on site or to get the hydrogen delivered and then compress it, store it, and dispense it. It had to refuel vehicles at 700 bar and do so from empty to full in about 5 minutes. The station had to be affordable, requiring a standardization of components to allow for mass production and thus economics of scale to kick in. Currently, stations are fairly expensive and mostly custom designed, although recently that has been changing. Beyond the design components and requirements, teams needed to develop a cost and economic analysis, which includes capital cost, operating cost, information about maintenance cost, and an estimate for the market price for the 5th, 100th, and 500th station. There's also a safety analysis, which needed to show ways to mitigate risks and list applicable codes and standards, and sections on operation and maintenance, and environmental analysis, and customer education and interface design. Next slide. So in total, we had 12 teams that participated in the contest from 7 countries around the world. And here you see the top 5 teams. And all the designs are available for download at the contest website under the 2014 contest section. So check out hydrogencontest.org. Next slide. And now I'm very excited to hand it over to the grand prize winning team from Washington State University, which will show you their design on their own slides. So Ian and Jake, take it away.
Thank you, Emmanuel. Welcome, everyone, and thank you for joining us today as we discuss our design for a drop-in hydrogen fueling station. I'm Ian Richardson, and also presenting the design with me today is Jake Fisher. We were the primary leaders of the Washington State University student team that won the 2014 Hydrogen Student Design Contest, and we were also the lead designers of the mechanical system. Both of our emails have been provided below our names. If you think of any questions after the webinar, please feel free to send us an email. We have also put a link to the contest webpage at the bottom of the slide where you can find the full report. Next slide, please. When designing a brand new station like this, you really need to consider the customer's concerns. In our situation, the customers are gasoline station owners. That's the most logical place to put these hydrogen stations for an initial rollout. From a gas station owner's perspective, the stations need to have a low capital cost, especially because the demand is still uncertain, and it needs to have virtually no maintenance so an owner doesn't have to pay a technician to come out to inspect and service the station. Besides maintenance and the initial cost, the regular operating costs also need to be minimized. This includes minimizing the cooling water demand and using 208 volt or lower power. These things will keep your monthly costs down and also increase the number of potential site locations. Since the station will initially be in urban areas where space is a premium, they need to have the smallest possible footprint so owners aren't losing parking spaces for other customers. Obviously, these stations need to be safe and meet all applicable regulations, but they also need to be visually appealing and catch people's attention. If hydrogen is going to be the fuel of the future, these fueling stations need to portray that. So with that, I'm going to pass it off to Jake.
Next slide, please. The paramount decision in our design was the choice of liquid hydrogen delivery to replenish our fueling station, so that's where I'd like to begin. We compared on-site electrolysis, on-site methane reforming, gaseous delivery, and liquid delivery based on operating costs, capital costs, transportability, and public impact associated with these technologies as they exist today. We found that our estimates match conclusions made in a 2013 NREL report that liquid hydrogen delivery has the lowest capital cost for a near-term mass deployment of 100 kilogram per day stations. We also found that liquid hydrogen is available in most metropolitan areas. In fact, it makes up 80 to 90% of all non-pipeline hydrogen deliveries. So a well-established infrastructure is already in place to supply our hydrogen stations. Next slide, please. So now that I've identified how we plan to get hydrogen to the station, I would like to talk about how we design the station around liquid hydrogen. These are some of the special considerations for a transportable fuel station that uses liquid hydrogen storage, different than what you'd see for a permanent hydrogen station design. The details of the safety system, design for transport, the liquid hydrogen storage tank, and how the station uses hydrogen boil-off are in the contest report, so I won't go into those details here. What I want to highlight is the thermal compression and how we incorporate it into the design. Thermal compression is the process of using the large temperature difference between liquid hydrogen and the environment to do work. Liquid hydrogen can be converted to extreme high pressure gas in a composite cylinder by allowing it to absorb energy from the environment around it. Next slide, please. The best way to explain how thermal compression is used and how the station operates in general is to walk through a simulated fill-up of a vehicle. So say a fuel cell electric vehicle comes to the station with a 25% charge of hydrogen in the vehicle tank. The customer connects the dispensing nozzle to their car receptacle. Next animation, please. First, hydrogen is dispensed from a medium pressure bank of cylinders, bringing the vehicle tank to 75%. Next animation, please. After that, hydrogen is dispensed from a single high-pressure cylinder, bringing the vehicle tank to 100% state of charge. Since the medium and high-pressure cylinders are stored at a cooling bath, in a cooling bath held at negative 40 degrees Celsius, dispensing only lasts 3 minutes, making the customer happy. After the fill-up, the station must recharge the medium and high-pressure cylinders for the next customer. This is where the station design stands apart from other designs and shows the cost savings. Next animation, please. A valve between the high pressure and medium pressure cylinders is open, partially depleting the high pressure cylinder and partially recharging the medium pressure cylinders. Next animation, please. The compressor turns on and pumps nearly all the remaining hydrogen from the high pressure cylinder to the medium pressure cylinders. This brings the medium pressure bank back to a full charge in the ideal case. The heat added by compression is dissipated in the bath, cooling the hydrogen to -40 C, and the medium pressure bank is ready to dispense again. Thermal compression is then employed to recharge the high pressure cylinder. Next animation, please. Liquid hydrogen is pressure fed into the cylinder from a bulk storage tank. The liquid hydrogen is then sealed off and boiled, creating a vapor at a pressure of 17,000 psi. By using thermal compression, the station can operate with a $60,000 6,000 psi compressor instead of a $100,000 12,000 psi compressor. It also reduces operational costs by using energy from the environment to boil and pressurize the hydrogen instead of electricity to run a compressor. Additional research on the liquid hydrogen filling process for the high pressure cylinder would help to optimize thermal compression, but is not needed for the design to work today. At this point, the station is ready to dispense. Next animation, please. Boil-off vapors from the bulk storage tank and those created from the liquid transfer process will be compressed and stored in a low-pressure cylinder. Next animation, please. The low-pressure cylinder provides hydrogen for the dispensing cycle if needed, and the fuel cell that generates electricity to power monitoring and safety systems in the event of a power grid failure. Next animation, please. So that is how the station is designed to operate. Now we'll look at some other features. Next slide, please. This is the remote operator interface designed by team members Simon Guo and Samusam Chanda. The stations are designed to operate autonomously, but for safety and reliability, a remote operator will monitor each station using the interface shown here. To the left side is the system diagram for the operator's reference. The right side shows sensor readings from the station in real time. Cylinder temperatures and pressures, as well as valve statuses, will tell the operator that the system is working and alert them if conditions exceed design limits or valves are operating out of sequence. If there is an issue with any of the components, such as an overheated tank, a warning message will appear here, shown in red, and alert the operator to check the system and take appropriate action. Next slide, please. Here again, the station is designed to operate autonomously, but interacting with customers via standard touchscreen tablet computer. The customer interface was designed by team member Patrick Fromm. Similar to a gasoline station, the user will select the method of payment, and a brief instruction on the nozzle operation will appear. The customer will be able to instantaneously monitor the fuel level and cost of the interaction. If at any time the customer has a question or is concerned about the system safety, the information tab allows for a live video chat with the remote operator and has the option of activating emergency shutdown procedures. Next slide, please.
This system has been designed to be as safe as practically possible. Each tank is fitted with a pressure relief valve to ensure they do not overpressurize. The trailer is ventilated with industrial fans to prevent any appreciable concentration of hydrogen within the container. The system will be continuously monitored in real time by remote operators, and fuel cells provide power to emergency and monitoring systems in the event of main grid power failure. The container is outfitted with state-of-the-art fire suppression and emergency warning systems to alert the public, local authorities, and the remote operators in the event of an emergency. If all other systems fail, the container is outfitted with an explosion relief panel to direct any explosion in a safe direction away from people and property. Next slide, please. Part of this contest was to find an actual location for the station and determine the necessary permits and regulations that would need to be followed. Miko McFeely and Brian Billow were the two primary members that worked on the siting and permitting. For simplicity, they sited our station on the Washington State University campus in the same parking lot as the motor pool gasoline pumps. This design meets all the applicable national fire codes and regulations for the selected site. If you look at the station footprint at the bottom of the slide, you can see the component layout in the 40-foot shipping container. The station is enclosed in an ISO 40 container so it can easily be transported and relocated with the changing demand. All the mechanical and electrical components are located at one end of the trailer away from the hydrogen to further increase the station's safety. The steel container walls are also lined with 2-hour fire-resistant panels to reduce the setback distances required in the NFPA codes. By reducing those setback distances, we increase the number of possible site locations and make it more appealing to the customers. Next slide, please. The economic analysis was fairly limited for this project given the fixed $7 per kilogram delivery cost and 100 kilogram per day demand, but our economists, Ben Smith and Austin Miller, took it a little farther to make it as realistic as possible. The key costs that were considered in our system are the fixed cost of $423,000, which is broken down in the pie chart and based on quotes or company estimates, and the monthly expenses including electrical power, cooling water, and maintenance. Note that we have not included the cost for a remote operator or the man-hours required to assemble this system. Our economists used this information to develop a fuel price model, which was simplified in terms of the required rate of return of the owner and the demand for hydrogen in kilograms per month. We used this model to analyze how fuel prices varied with the changing monthly demand and the required return. Next slide, please. With a reasonable demand, our results show that hydrogen is comparable to the cost of gasoline. In the table, you can see the price per kilogram and per 5 kilogram tank calculated with a return of 10 and 30% and a monthly demand of 3,000 and 6,000 kilograms. The plot below is just a graphical representation, but it does show us that the price is much more dependent on the demand than it is on the required rate of return, and it begins to level off just above $9 a kilogram as demand continues to increase. So these results show that a station that services just 50 vehicles per day, which equates to 6,000 kilograms a month, can dispense fuel for $48 per 5 kilogram fuel tank, which has a range of roughly 300 miles. This is equivalent to a vehicle that gets 25 miles per gallon at a gas price of $4 per gallon. Next slide, please. Since presenting our design for the competition back in May, we have been working to get a prototype developed and funded. We have partnered with GP Strategies on a DOE proposal to develop the cryogenic thermal compressor, which is the key compression and energy-saving portion of this design. We are also redesigning a smaller single dispenser prototype station that would potentially be used on the WSU campus to fuel a new university shuttle bus. And we're also in negotiations with a couple other companies to develop a prototype station that could be used for mass production to support the initial hydrogen vehicle rollout. Next slide, please. In conclusion, a hydrogen fueling station has been designed for $423,000. It uses the existing liquid hydrogen infrastructure that is well established and already in place. This design utilizes thermal compression to reduce operating costs. The station uses state-of-the-art emergency systems to ensure public safety as well as equipment safety. And most importantly, the system is made from entirely commercially available parts, so there's no reason the system couldn't be built today. Thank you.
All right. Thank you so much. Again, if you have questions right now, please type them in the questions panel on the control panel on the right-hand side. If you don't see it, you may need to click on the little red button to open up the panel, and we'll get to the answering of the questions at the very end of the presentations. And next up, we have the Honorable Mention Team, Humboldt State University. Julian, it's your turn.
Thank you, Emmanuel. Hello, everybody. Today we are here to present Humboldt State University's design for a drop-in hydrogen fueling station for a gaseous delivery system supply chain. Our names are
Solomon Clark,
Anthony Egink,
Matt Nyberg,
and Julian Quick. Our email address is listed in this title slide if you have any questions after the presentation. We are happy to answer them. This competition was a great opportunity to learn more about the hydrogen industry, and after this competition, we are all enthusiastic about the future of the hydrogen industry. Next slide, please.
So first up we have our design goals. When we were designing the station, we wanted to think about several objectives which we want to achieve in the design of our station. The first of these objectives was a modular and easily transportable design. This was so that the station can be quickly installed at several different locations. We also wanted the station to meet Fast Fill SAE TIR J2601 compliance standards, and this is for a 3 to 5 minute fuel time as well as customer safety. We also wanted the design to have minimal site preparation. This is so that the station can be quickly installed at several different locations. We also wanted to incorporate comprehensive safety features. This is to protect our customers as well as to protect the reputation of the hydrogen fuel industry as a safe fuel alternative. And in addition to this, we also wanted to incorporate only off-the-shelf components, and this is to demonstrate that this station could be built today. We also wanted to minimize costs to industry and consumer, and this is to make hydrogen fuel not be a cost-prohibitive fuel source. And in addition to this, we wanted to connect the California Hydrogen Highway. We live in California, and there is several hundred miles between Northern and Southern California where there are no hydrogen fueling stations. And with this low-cost and highly transportable station, we are interested in being able to connect those two halves of the hydrogen highway. Next slide, please.
For the station layout, as you can see on the left side of your screen is an aerial view of what a typical installation might look like. On the far left is the consumer access point, indicated by red arrows, and that's where vehicles would drive up and be serviced by the station. Directly to the right and below the vehicle access point is the shipping container housing, and that houses all the station elements. And then our storage and delivery is on the bottom right with a tube trailer and with multiple stalls for trailer switch out or for an increased storage. We also wanted to consider that not every location would be suitable for delivery. You may be near a pipeline, or you may want to produce the hydrogen on site using electrolyzer. So with minimal modifications, the station could be used in any of those situations. Next slide, please.
Gas is delivered in a compressed hydrogen tube trailer. The gas is then compressed and cooled through a cascading storage and system and delivery system on an as-needed basis. The compressor necessary to raise the gas to the appropriate temperature, to the appropriate pressure for the cascade cooling system has a minimum inlet pressure of around 100 bar. In order to maximize hydrogen extraction from the tube trailer, we use a tube stage compression system with a low pressure compressor and high pressure compressor. Next, the cascade cooling system is stored to -10 degrees, and the gas is cooled inline from the cascade storage system to the dispenser to -40 degrees before it is dispensed to the hydrogen vehicle. Next slide, please.
Here you see a system schematic showing the basic flow route and compression and storage throughout the system. It starts with the two-stage compression that Julian was just speaking of from the trailer, which maximizes the source use. Then it travels to a cascade storage system.
Thanks, Andy. This is Matt. So the purpose of the cascade storage system is to optimize compressor efficiency, since there's no point in compressing all the hydrogen clear up to 900 bar except when needed. So for partial fills and early parts of the fills, the lower pressure tanks would be used, and the higher pressure tanks would be exclusively for the higher pressure in the top end fills. Also, what the cascade system allows is, as the hydrogen is depleted from the lower pressure tanks and the higher pressure tanks are moved on to, the tube trailer compressor can begin to fill the lower pressure tank so that the next car it's prepared for the next car when it arrives.
Thanks, Matt. Cooling for the system takes place in two stages. The Cascade storage system is housed in a refrigerated box, basically, which is a small box inside the station that's well insulated, and this box is maintained at a negative 10 degrees. And that allows you to cool it to negative 40 relatively easy using a second stage for the cooling system. This would then travel to the dispenser for the fast fill dispensing, and there's also a booster compressor in the system in the event that there's any pressure differences. Next slide, please.
So here we have the station costs. It's broken up into several major components, which would be the cascading storage system, several compressors, the dispenser, safety equipment, and other equipment including installation. The total cost for the station was initially estimated at just below $1 million. Since this time, we have had a more accurate price quote on the dispenser from Bennett. This brought the price down from $300,000 to $85,000, bringing the total price closer to $750,000. Next slide, please. So here we have our station economics. This is where we did an analysis of if the station were to be mass-produced and what the payback period of the station would be. Initially, the station cost is around $1 million, and by the time 500 stations are produced, the cost comes down to about half of that at $457,000. On the left here, on the bottom left, you can see a graph of the net present value as compared to the year. In the middle of that graph, there's a 0, so you can see that as the years increase, your profit breaks even, and then you make profit out of that. With one station, the payback period is approximately 6 years, and with 500 stations, the payback period is approximately 4 years. The payback period of our station is highly dependent on the price of hydrogen for the consumer. On the right, you can see a graph of the price of hydrogen compared with the payback period. And we chose a price of around $9 a kilogram of hydrogen. This is because before $9, the payback period sharply increases. But if the price is any higher than $9, it does not dramatically affect the payback period of the station. So our objective here was to create a low-cost station with a short payback period, and it does have significant mass production value and also keeps the price low to the consumer. Next slide, please.
So we wanted to be comprehensive about safety in this, as we mentioned, to protect the customers and the hydrogen industry as a safe fueling alternative. So there will be a PLC, programmable logic controller, that monitors pressure and temperature primarily, because those are two big indicators of potential problems. There will be a waterless fire compression or suppression system that is independent of power supply. There is a hydrogen sniffer that will, upon 1% detection of hydrogen, it will initiate to the normally passive ventilation system a fan that ventilates more quickly, followed by a 2% inaudible alarm, as well as sending a message to the controller. There will be pressure sensors to monitor pressure that will indicate both leaks, and in the case of leaks, there are isolation valves to close off the tanks from where the leaks might be. And there is also pressure relief valves for the cases of runaway compression or elevated temperatures causing higher pressures on the tanks. There will be an electrical emergency throw switch on site, as well as the ability to remotely disconnect from power. In the event that power is lost, there will be a battery backup for the PLC, the sensors, and other safety equipment. Let's see, in the event of power loss, there are normally closed valves so that if there is no power, all valves will close. And further, in the event of a loss of communication, the entire system will shut down.
Next slide, please. So to wrap things up, we're just going to talk about our design solutions. And we broke this into 2 points, market solutions and technical solutions. Market solutions are important in that we need this to be available now. We have fuel cell electric vehicles rolling off the assembly lines and ready to be used today. And so in order to do that, we evaluated the best way that the industry and the consumer could enter the alternative fuel market in a cost-effective manner. And one of the ways for the industry is that this design uses the existing infrastructure, and it allows for industry that's already in production to just expand what they're doing. And the gaseous delivery allows for a low cost and existing infrastructure is utilized.
Good points. We also wanted to highlight the technical solutions of our station. Our robust design allows for special cases. For example, maybe there's not enough space to have the tanks, the tube trailers deliver hydrogen. In that case, an electrolyzer could be used. Or maybe there's a site where methane reformation is most appropriate, and that could just be connected to the station instead of the compressed hydrogen trailer. This station uses strictly off-the-shelf components, and we believe it could be built today. And it does meet a fast fill 3 to 5 minute fueling time by cooling the gas to sufficient temperatures and high enough pressures. Next slide, please.
We just want to say thank you to everybody that helped us with this presentation. Thank you to the Hydrogen Education Foundation and the Department of Energy. We're really excited about what we've done, and we appreciate the opportunity. Emmanuel?
Hey, thank you guys so much. I want to remind attendees that you can type your questions in right now, but we will wait until the end. You know, I've been fortunate enough to meet some of those team members, some of the people that have just talked, and at the ACT Expo 2014, and it was an honor to talk to them and see their designs and all the work that they've put into it. I think it really shows. And if you're interested in reading their entire presentation, just go to the contest website and you can download their design there. So next slide. I want to take the opportunity right now to transition into the 2015 contest and provide a brief preview of that. It will be launched shortly, and unlike most previous contests, the 2015 competition will have a stronger business focus. The topic will be developing innovative hydrogen fueling station business and financing models. And we have support from the DOE's Fuel Cell Technology Office, the NREL, and Toyota Motor Company. But of course, we're always looking for additional industry collaboration for this very important topic. So if you're interested, if you're in a company, if you're interested, please contact me after this webinar or fill out the survey and indicate any interest right there. My information is also provided on the contest website. And to provide you the backdrop for the 2015 contest theme, I'll hand it over to Erica to introduce my colleague, Connor Dolan. Erica?
Thank you. Yes. Connor Dolan is the External Affairs Manager for the Fuel Cell and Hydrogen Energy Association, also known as FCHEA. As the External Affairs Manager, Connor oversees the association's communications activities and facilitates association member programming and events planning. Connor has previously worked for the Methanol Institute and the U.S. Fuel Cell Council. Connor?
Yeah, thank you for having me on today. I really appreciate the opportunity to provide some input, and thanks to HEF and DOE for putting this opportunity together. Can you go on to the next slide? So H2USA is a public-private collaboration co-launched by the Department of Energy and Industry, whose mission is to promote the commercial introduction and widespread adoption of FCEVs, fuel cell electric vehicles, across America through the creation of this partnership. We're working to overcome the hurdles of establishing hydrogen infrastructure. We currently have 36 participating organizations, as you can see on this slide, including the federal government, state agencies, automakers, energy companies, fuel cell and hydrogen suppliers, nonprofits, national labs, associations, and others. As you can see, we cover the broad range of FCEV and hydrogen infrastructure supply chain. As you may know, significant effort is currently underway in the state of California to develop hydrogen infrastructure within the state, providing up to $20 million per year through 2024 to develop at least 100 hydrogen stations. By the end of next year, there will already be 50 hydrogen stations built in California. The large issue that H2USA is tackling is expanding that infrastructure beyond California to the rest of the United States. We recognize that not every state will be able to provide significant government funding to help jumpstart the development of infrastructure. That is why this contest is so important to the industry. Finding innovative station and financial solutions to advance infrastructure will be a huge step forward in enabling further development of fuel cell electric vehicles. With Hyundai already leasing their Tucson FCEV in California today, Toyota and Honda set to launch their vehicles next year, and more automakers preparing their vehicles in the following years, the time is now to begin developing the necessary infrastructure to fuel these zero-emission cars. And with that, I will kick it back to you guys. Thank you.
Hey, thank you, Connor. And if any of the attendees that want to see some of those cars in action are in California, feel free to sign up, attend the Fuel Cell Seminar, which is next week. There will be some cars to test drive, or just sign up for HEF and other association updates. There are ride and drives all across the country, and you can experience them firsthand and get to drive one of those zero-emission vehicles. So at this time, I'm happy to discuss the sections for the soon-to-be-launched 2015 contest. The contest will have about 4 sections, and the basic principle, as we've just heard, is for participating student teams to conceive a financially sound business model that will allow a hydrogen fueling station to be deployed and operated without government incentives. In order to do so, the teams need to assess all cost and revenue streams. For example, starting with the technical station design, teams have to assess what functions and services the station should be able to provide, what kind of revenue streams those may produce. For example, should the stations be able to produce electricity during times of low hydrogen demand, but times of high electricity prices? What are the costs associated with such, including such features? As always, we encourage outside-of-the-box thinking for these contests, and this is certainly one of them that can use that. So to better understand the challenges, teams have to create a strength, weakness, opportunity, and threat analysis. And the meat, of course, lies in the economic analysis, looking at innovative revenue models, managing uncertainty and risk, and as mentioned, defined other applications for the use of hydrogen when there is potentially low demand. And finally, the teams have to develop a marketing plan. So while there are several phases, at the end, the top teams will be invited to attend a venture forum to pitch their design to a group of investors. And in order to ensure that the teams start with the same assumptions, the Hydrogen Education Foundation will provide information on vehicle numbers, fuel, and basic station cost. So next slide. We'll have more information once the contest is officially launched. So check the website, hydrogencontest.org. And as I mentioned, Sign up for our news lists or subscribe to our Facebook page to receive timely information on the launch and other information. Now finally, the proposed timeline sees a December 8th early registration deadline and the January 16th final registration and abstract deadline, and the final business plan submission deadline of May 4th. We hope that this allows the student teams to finish their plan before the weeks of finals, and the investor forum then will be about the beginning of June and the final award ceremony after that. Next slide. So I think we're at the end of the presentations. We're ready for questions, but meanwhile, check out the contest and the H-Prize sites. Like us on Facebook. Make sure to take the survey at the end of the webinar. And with that, back to you, Erica.
Thank you. So we have a few questions that have come in. Feel free to continue to add yours. We'll start with a question for the Washington State team. The question is, does the $423,000 include equipment assembly and installation on site, or is this just the cost of the parts?
So that $423,000 is just the cost of the components themselves. So they would be brought to a central location and assembled in a shipping container and then trucked out to wherever the site location would be from there.
Thank you. Next, we have another cost-related question, and this is for the Humboldt team. The question is, are you able to provide the name of the supplier for the $85,000 dispenser?
Yeah, we spoke with a representative from Bennett at the ACT Expo when we were there in Long Beach in May, and that was where we got that estimate from.
Thank you. Another question for the Washington State team. First, they said, excellent job and thinking for the effort. They'd like to know, why did you opt to put all of the equipment in one container instead of two containers? Is this practical? Will there be room to do repairs on the equipment in the container?
Well, thank you for the compliment, first off. And one of the biggest reasons that we went to a single 40-foot container was due to size restrictions. So a lot of gas stations don't have the space to put anything larger than a single 40-foot container, especially when you have to factor in the delivery to get a tanker truck in there. So we really wanted to keep it in an ISO 40 container so you can put it on the back of a semi-truck, truck it into a location, unhook it, and then plug it into on-site electricity and power, and it would be ready to go. So that 40-foot station is designed to hold 3,000 gallons of liquid hydrogen, which is right about a week's worth of hydrogen for a 100 kilogram a day demand. It is pretty cramped in the container itself, but there is room for a person to move around to get access to the valving manifolds and the plumbing and the other tanks. And all of the electrical machinery that is most likely to need maintenance or have issues with it is up at the front of the container, so it's easily accessed just through the regular doors.
Great,
so I
thank
hope
you.
that answers the question.
All right, another question back to the Humboldt team about the $85,000 dispenser. The question is, did that pricing require a volume purchase, and does it include metering?
We do not believe that it required a volume purchase. We didn't get into detail about a volume purchase at the time, but it was our understanding that it did include metering. Of course, it didn't include any type of pre-cooling because we had already designed that into our system.
Thank you. All right, another question for both teams. Let's start with Washington State. When you considered the price per kilogram of hydrogen, did you consider any taxes or other highway or fees?
So the price of $7 a kilogram was actually specified in the project, or in the contest outline, and that was just to level the playing field so that it would be a constant price for all of the teams in the contest. So we didn't actually choose that.
Thank you. Here's another question for, how about for Allie? When will copies of this presentation be available?
Great question. We typically give us about 10 business days. Sometimes it'll be up sooner than that. So that's why I send an email once we have those up on the website. But plan roughly 10 business days.
Okay, thank you. Another question for the Washington State team. In the early market, when you don't have high volume vehicle demand, how long can your station stay unused before you lose hydrogen due to boil off?
So the station is always losing some hydrogen due to boil off. So when you have that liquid hydrogen in a storage tank, it's always boiling just due to the temperature difference between the atmosphere. And the rate of that is about 0.3% per day. So it depends on how much volume is actually in that tank, but it could last several weeks without actually running dry if it's full. And with that boil off, we do recapture that and store it into either the medium pressure tank or the low pressure tank, so we're not actually losing that hydrogen. We're not venting it to the atmosphere unless we actually absolutely have to.
Okay. All right. A couple more questions here. For the Washington State team, what is the timeline for follow-on work? And it looks like they're referring to developing your technologies and partnerships.
That's a really good question. So the DOE proposal that was submitted, I think there's still a few months until we find out what is going to happen with that. As far as the relationships with private companies, they're in the process of pitching that to their venture capitalists and their investors. So we're kind of working on some redesigns and modifications to it, but we don't have a hard timeline on when they will get back to us on that.
Okay. Returning to the question about including everything in a single container and the practicality of it, there's another question around fitting the containers into differently shaped gas station footprints, and also related to the potential to expand to larger liquid hydrogen storage capacity. Also about separating, I guess there's a few questions here just in general about why you chose to put everything in the container, more related to the footprint and separation between liquid storage and electrical.
So I'll try to answer some of the main points, I think, and keep reminding me of the questions if I get off topic. But the footprint, just the reason it's in a standard 40-foot shipping container was just for the transportability aspect of it. So you can bring it into a location and unhook it, and it's ready to go in 24 hours. There essentially is no installation except for plugging it into the grid power and connecting it to water, on-site water. You can increase the storage capacity. They do make larger liquid hydrogen tanks, but it just simply wouldn't fit in a shipping container. It would have to be its own trailer that would get trucked in, similar to the Humboldt team's design, where you have a separate liquid hydrogen tank sitting next to your actual station.
And I'll add to that these are modular, so you can bring in more than one station to a site. So each station has 2 dispensers, and if you want to expand, say you have a higher demand, you just bring in another trailer, and now you have 4 dispensers.
So is there any other part of that question that we didn't address?
I'll see if the person asking adds anything else. I'll let you know.
Okay.
Question for you on the reliability of these tanks under the cryogenic cycles that they'll be seeing. So when you're using thermal compression, the tanks are being subjected to, 20 Kelvin liquid coming in and coming up to minus 40 C of the cooling bath, correct?
Yes, that's correct.
What data is there to support the tanks you've chosen in that application?
So it is a fairly new kind of industry going into it. They use a lot of their Type 4 pressure vessel tanks, so they have a composite lining and they're carbon fiber wrapped. And there's quite a bit of data for like liquid nitrogen temperatures, so if you get up around 70 or 80 Kelvin, but traditionally there hasn't been a ton of research into liquid hydrogen applications.
I'm pretty sure there's a report done by Lawrence Livermore that has cycled composite tank. I think it's been several thousand times without any structural or cracks or anything, any issues that they've seen.
Yes. So from what we've talked to with manufacturers, as long as you keep it within the pressure limits, it doesn't affect the fatigue life all that much, and they run it out for thousands of cycles and haven't experienced any issues yet. But as far as a cycle still failure, I don't think that's well understood by the industry at this time.
All right, thank you. And I saw that the person who asked the last question about footprint and the layout says that the answer is sufficient. Thank you.
Okay.
There are no more questions at this time, so if anybody has something that comes in later, you're welcome to contact our presenters. Their email contacts are provided in the presentation, and as Ali mentioned, these will be available with the full webinar recording online in 10 business days. Ali, I'll turn it over to you to wrap up. Thank you all so much for presenting.
Yes, thank you guys so much. It's always a challenge to work with multiple schedules. So thank you for making the time available to do this. And we appreciate everyone who called in, and we encourage you to get on our website, sign up for our newsletter, and come back to future webinars. So thank you guys so much.
No, thank you.